All righty, and welcome back. Next up is our presentation from Sudeep Pillai of Toyota Research Institute on MLOps for high-stakes environments. Enjoy.
Hi, good morning. My name is Sudeep Pillai. I lead the machine learning engineering team here at Toyota Research Institute, where we develop Toyota's next generation L4 vehicle. And yeah, I'm excited to talk about MLOps for automated driving. So a little bit about who we are. We were established back in 2016 with $1 billion budget. Now grown to about 300 plus employees across 3 locations. The main focus areas have really been on automated driving, household robotics, advanced material design and discovery, and machine-assisted cognition. So at TRI, we sort of have a unique approach to automated driving where we really believe on this idea of one system, two modes. So the idea is that we have what we call chauffeur, which is the kind of self-driving technology that you've probably heard about in the press, specifically an approach where we're essentially trying to replace the human driver with the machine. And essentially, this removes the human from the driving equation. Well, it's a wonderful goal, right? Sometime we may achieve it. Someday we may achieve it. But it's essential not to underestimate how hard of a task chauffeur and chauffeur systems are, both technologically and sociologically. Now, the alternative is a Guardian, where we really focus on focus on the same underlying software architecture, but essentially the idea is to amplify human control of the vehicle and not replace it. So with Guardian, the driver is meant to be in control of the car at all times, except in those cases where the Guardian anticipates or identifies a pending incident and employs sort of a corrective response in coordination with the driver input. An eventual goal here is to create a car that is almost incapable of a crash. So we really think this one system, two modes really sets us the stage for where we're headed in terms of automated driving for Toyota. So now I'd like to talk about the machine learning that's happening within automated driving more generally across the industry. And what we're seeing today is that machine learning is really eating AD software. And by that I mean AD software, automated driving software, was traditionally hand engineered. So there were it was modular just to make things a lot more composable. There were a lot more rule based back in the day. But because of these reasons, right, they were fairly rigid. It was hard to really configure them and actually be data driven. So it turned out that they suffered in terms of being able to learn from a lot of new experiences, and also, as a result, sort of generalize poorly. Now, as we're moving more towards this, software 2.0 world, right, going from 1.0 to 2.0, you're really starting to see the same kinds of, techniques being used even in automated driving. So in a typical AD stack, you have perception, prediction, planning as sort of the core competencies for automated driving, and you're starting to see a lot of these technologies sort of adopt machine learning. And as I was saying earlier, right, we're really starting to see ML sort of eat away even into the AD driving stack. So just to give you an idea, right, the perception stack back in 2014 turned out that almost everyone used deep learning and machine learning for these. Fast forward to 2017, you're starting to see machine learning across a lot more of that AD stack, and we really think that the future is going to be where it's sort of this blended control with perception, prediction, and planning all being fairly driven by machine learning. And in fact, I think the real idea here is that how do you go about building generalizable machine learning that is data driven and allows us to really scale to diverse situations and scenarios. So to give you an idea or flavor of the machine learning in our perception stack, here's an example of the 6 cameras that we have in our stack with their semantic segmentation up. So essentially pixel-wise segmentation of the scene. And we sort of paint that world into the 3D LiDAR point cloud that we get out of the sensors in the car. So this is sort of that internal representation that the car has in order to do prediction, do planning. And so this is sort of an example where we're sort of composing together multiple machine learning models into a single perception framework. So now a few more examples of this. Right, here's another example of 3D detection with velocity estimation. All of these sort of capabilities are now driven by machine learning and deep learning techniques, and it's sort of now almost ubiquitous in an AD stack with this sort of core ML technologies. Even in prediction, we're starting to see these days with sort of dense traffic maneuvering, you're seeing the predictions of trajectories of ADO agents. So like all the other agents in the scene, you're seeing the predictions over a 1 second time horizon. You can start to see even pedestrian prediction. So as we interact with pedestrians, we identify the pose of it, track where they're about to go next, and only then safely pass them, say in crosswalks such as this. So the real idea here is that as we're trying to build this complex system, right? What ends up happening is that we really need to think about, as we build these complex systems, but also work on specific targeted machine learning models, such as say 2D detection, 3D detection, semantic segmentation, for instance. How do these sort of compose together into a system level framework? And as we deploy these models, right, how do we build safety first into the deployment aspects of these models? So this is really what motivates me to talk about machine learning ops for automated driving, in that it's important to think about what that infrastructure looks like for automated driving, right? So if you think where ML code really accounts for that small fraction of that machine learning engineering infrastructure, it's more so true even in automated driving. As we build sort of these domain-specific tools for automated driving, we realized that it turned out that what we thought we were going to build to what we actually needed to enable machine learning in automated driving turned out to be a lot more. So I wanted to give you a few ideas as to what this meant in terms of adapting some of these technologies to automated driving and what a life cycle looks like within automated driving. So the real goal here is that we want a unified platform for accelerated fleet learning, right? We want to take sort of inspiration from the Toyota production system for vehicles, right? Where you can think of this as an assembly line that Toyota has and wants to optimize the assembly line to produce more vehicles, on a day-to-day basis. We want to think of that sort of analog, but in the context of machine learning models as we deploy. So we want them to be domain specific in that these are very much targeted towards automated driving. We think that some of these sort of pipelines or capabilities are more generalizable to even robotics settings. But really, we want it to be model agnostic. We want to be able to try deploying different types of techniques and different types of models into the same framework. And at the end of the day, we want these to apply across heterogeneous fleets. So the goal here really is to try to see how do we merge or how do we marry MLOps best practices with sort of the safety guarantees that you need to deploy into automated driving settings. And really, at the end of the day, we want to codify all of these so that things are a lot more streamlined. So the way I think of it is like, what is the fleet learning operations as code framework that we want to build and develop so that we streamline model deployment. So what I'd like to talk about here is really saying, how do we go about adapting ML ops for automated driving, right? So the way we think of it in terms of the challenges that are involved in building these complex systems, it turned out that machine learning ops or ML ops, in the 3 different phases that you're seeing on the right, there were certain key challenges that we faced as we were building these systems for automated driving. And I'll touch on each one of these individually in the subsequent slides, but all I wanted to point out was that there are considerations at the design phase where we talk about model versus system behavior. There are considerations within model development in terms of complexity of how you go about composing different models into one big robotic framework. And even complexity in terms of operation. I think there is an additional operational burden for safety critical applications, right? We can't be deploying things every minute because we have to test these things, and sometimes testing actually takes a fair amount of time, both compute wise, but also making sure that this is a physical platform that we're deploying to, and we don't really hurt people while deploying new capabilities. So this is sort of, the first thing I wanted to touch on was this notion of model versus system performance. So I'll go over this pipeline real quick, but what I wanted to talk about was essentially if we were to think of how we go about improving models, right? We have some notion of a log replay, which is essentially showing what that internal representation of what the car sees in the world. As a developer, you'd say, okay, let's improve performance of cars at intersections, and that's really my goal. And at the end of the day, I want to deploy a new model that does this, that achieves this, right? Along the way, we can think of, we want to be able to curate specific scenarios where, I'm at intersections, I see cars, and I want to identify, difficult situations so that I can learn from those difficult situations. There's obviously the labeling step, right, where we look at, QA quality once we've labeled these objects, scenarios, and we want to really measure these as a mechanism so that, at the end of the day, we're showing monotonic improvement in performance, both in the model sense and also as a system. In terms of training, right, we're looking at various different metrics, MAP, MIOU, or average position in IOU, for instance, or several other downstream model metrics and system level metrics. Once we get to deployment, we're looking at things like simulation testing, there's regression testing that I'll refer to in the next slides, but really there's a whole suite of tests and benchmarks that we go through before we even get to the point where we stage these models for deployment, right? So now at the end of it, what we really measure in terms of system level performance, I think you've probably heard this metric more, which is a lot more popular in industry, which is this kilometer per disengagement, right? And now how do you relate something as a system-wide metric as kilometer per disengagement with the original intent, which was, I want to improve performance on cars at intersections, right? And this is really where what we're thinking of is like what we're trying to improve our model performance, whether it's the 3D detection, whether it's 2D detection, something else, a very targeted ML model. But what we're measuring at the very end is the system level performance. And really we need to think about the trade-offs as we improve models. What are the implications on a system level? And in some cases, we need to prioritize system level performance more so than purely on the model front. Here's another example of this complex, model dependencies that we have. So in terms of, as we build sort of robotic systems, we want to make sure that things are modular, things are composable. And in some of these cases, as you have more machine learning across the stack, what ends up happening is that now you have models that are trained on predictions from other models, right? So an example of this is, say, we wanted to update model G, right? We want to update the weights or update the model to improve performance on it. Turns out that we can just retrain this model and everything else remains intact. There are no issues here. But what if we had to retrain a model which is further upstream? We really need to think about what the downstream models that actually get affected by this, just because of the dependencies that are enforced through this architecture, right? And not only do we have to look at model level metrics, which is like model A, D, E, F, and G, but we also need to think about the reproducible metrics or system level metrics to say, do I monotonically improve performance across all these parameters, right? And it's important that in some cases, what we find out is that certain models actually regress, but the system level performance actually improves. So we've got to make those trade-offs, and in most cases, it's never a simple decision. And so we have to constantly think about, both on the architectural stand and from the design standpoint, but also in terms of what metrics are actually important to drive, improvements. And finally, I want to talk also about this notion of safety and how we impose sort of safety critical applications, how we impose ML ops in safety critical applications. So an example of this is, as we deploy new models, or as we sort of have these candidate models that we train, we go through a suite of regression tests. So, once you have the candidate model, we go through a system level evaluation where we look at end-to-end evaluation metrics. Their system performance benchmarks, so runtime performance, whether these models actually run within the time slot that they're provided, right? You want to make actions fairly quickly. You don't want to wait too long before these predictions are made. So you need to have runtime checks and stress tests. You have regression scenario testing. So I want to be able to operate well in intersections. I want to operate well in highway scenarios. So we need to have this diverse set of scenarios and make sure that we actually, anytime we make a code change, right, it applies, the improvements not only apply to one scenario, but across the board. And finally, we want to augment all this real-world testing because it is challenging to test purely with real-world data, because these typically involve, in some cases, involve also labeling, which is an expensive effort. So if we really want to scale up things, right, we can actually start simulating, right, and simulating both in the closed loop setting, but also sort of fuzz testing and just getting more scenario coverage. And we can do a lot of these with sort of modern simulation tools today. Finally, once all these tests have sort of passed, now we can think of staging these models, right? And what we go through is this notion of a safety certification so that we can actually do closed loop testing. So this is essentially, in a closed course, we have the car tested with all the models, updated, for instance, and only after you've passed each of these steps do we really get to a public testing deployment, right? So there's several layers of safety involved before the model actually gets deployed into a fleet. So to finish off, I really wanted to talk about this notion of accelerated model iteration. I think the real goal here is that what we hope to achieve, or what we hope to build, is really this unified and scalable infrastructure for fleet learning, right? At the end of the day, if you think about this whole life cycle, there, as we deploy new models into the vehicle, right, there are different timelines for different tasks. If you think of ingestion versus labeling versus training, right? Sometimes labeling can take weeks. Sometimes training can take days. Whereas we have cars out there on a day-to-day doing day-to-day operations, giving us reports and metrics. So at the end of the day, right, the name of the game really is that fast iteration cycle. We all know about the heavy tail in automated driving, right? Which is, it's extremely difficult to find those special cases. You have to drive a lot of miles to get those special cases, or the heavy tail, to encounter the heavy tail. And so the only way we can actually react and improve models on these heavy tail is to really be able to iterate fast, right? Be scenario driven. But at the end of the day, deploy all these models with sort of safety first guarantees, right? And where we really want to see this grow into is sort of this foundational capability for learning from Toyota fleets. Today, we're talking about a very finite set of L4 vehicles within at TRI, for instance. But very, very soon, this is going to be a fleet of Toyota vehicles in the millions, collecting data and actually allowing us to train from an extremely large fleet. And so it's important to not only be able to build this unified platform, but actually scale to that sort of level of data, sort of this data firehose, if you will. So yeah, with that, I wanted to conclude and say, we're doing a lot of cool things at machine learning at TRI. We have both an engineering team, which is the team that I lead, where we more or less design, develop, and operationalize most of these machine learning models for safety critical automated driving. And we also have a machine learning research team where we really fundamentally believe that safe autonomy is still a scientific problem. So we work on problems ranging from holistic scene understanding to self-supervised learning and even differentiable rendering. So specifically looking at, how do we try to augment our current modeling frameworks with fewer data or lesser data, because as we really scale to the Toyota scales of things, it's almost impractical to be labeling every single sample that comes out of a Toyota vehicle, right? So even though we believe today in supervised learning, we really think that the future holds in the self-supervised and semi-supervised regimes, and we really can learn sort of a label-efficient manner, at scale. And so we've really been looking at self-supervised learning and even sim to real as sort of the core competencies that allow us to unlock the Toyota's data advantage. So yeah, with that, I want to wrap up and say we are hiring, so feel free to reach out to me, and with that, I'll take any questions.
All right, Sudeep, thanks so much for your presentation. Awesome job. We've got a couple of questions, several questions coming in. A lot of interest in this idea that you talked about in terms of your model level optimizations and your system level optimizations. And one question in particular from Aman: how do you trade off model level metric improvements with system level metric regressions if you encounter that kind of situation?
Sure, yeah, absolutely. Can you hear me just fine?
Yes.
Okay, great. Yeah, I think that's a great question. I think in most cases, as I had mentioned in the talk, we care really about the system as a whole performing well, right? So in a lot of the cases, we want to ensure sort of monotonic improvement in performance on a system level, even if model performance in some cases. So we've had instances specifically where model performance doesn't necessarily improve or almost like plateaus, but the model in fact gets better generalization, right? Better robustness, in that it actually trickles down into a better system level integration. Right, so in some of those situations, we actually see an improvement in system level performance, but we actually don't see much of a, some of those cases we want to get those kinds of models through because we want to improve sort of robustness in general. I would say that in most of these cases, it's sort of a signal in one way or the other. In some cases, these are better models that are more robust. In some cases, we need to really look at what are discrepancies between system level data sets, right, versus model level data sets. So we have sort of validation sets that are very model specific, model centric. We also have data sets that are system level. And so in some cases, it also means that maybe our model level data sets aren't complete enough, right, in terms of diversity, in terms of robustness, to basically signal that we need to collect more diverse situations to ensure that model level metrics also give us a valuable signal. So yeah, I'd say in most of the cases we do sort of prioritize system level metrics, but model level metrics are the fastest feedback cycle for us to improve on. So we sort of look into both at the same time.
Got it. And a related question to how does this interplay with the platform and any automation you may have in place? Do you, for example, does this complicate automated retrains if you're doing that, or do you stick to manual processes?
Yeah, so I think as I mentioned, right, the real sort of the name of the game is iteration. So we do want to automate as much of that stack as possible. The parts that we cannot automate are in fact those safety certifications and sort of the final closed loop testing where the person actually sits behind the wheel and actually drives the vehicle. But we do want to get to that point where we can automate as much of it as possible, where we deploy a new model, we'd run all the system integration tests, have all the metrics sort of at our fingertips or sort of on a dashboard, so that we can actually start comparing, and then we can sort of have a final human in the loop to sort of stage that into closed loop testing, and that's sort of the final goal. That we do want to automate as much of it as possible, so that we sort of speed up the iteration cycle.
Mm-hmm. So Josh is asking about model acceleration through things like TensorRT and that has trade-offs. Are those things that you do?
Yeah, I think that's a great question.
And also, how do you validate them in the process?
Right. Yeah. So in the same light, right? We think of these as we want to have model validation performance. As soon as they're trained to once they've been trained, we go through in some cases quantization, distillation, or even as Josh mentioned, right? The sort of TensorRT optimization, right? So post TensorRT optimization, and we do TensorRT sort of heavily within our stack. Even after TensorRT, we sort of deploy that model and look at system level metrics. And in fact, most of the system level metrics that we gauge are in fact as a result of composing together multiple TensorRT models. So the system level performance actually do indicate post optimization as a full system as a whole. So yeah, we do look at that, and it is fairly integrated into our stack. What's I think slightly more involved is that TensorRT, for instance, are very GPU specific or sort of target architecture specific. We train in the cloud, but we want to deploy onto our vehicles that have potentially different GPUs on them. So we do actually go through a life cycle where we deploy them into a rack that effectively emulates our vehicles, so that we basically get the one-to-one comparisons with what would happen on the vehicle versus what happens sort of virtually on the cloud. And so yeah, we go through all these to look at those system level metrics, and they do indicate.
You mentioned simulation. Is simulation used earlier in the process, or do you use simulation post deployment as well as you're evaluating those models?
Usually it's pre-deployment. So, part of that, pre-merge sort of evaluation, even pre-merge, they're fairly rigorous in ensuring that, the models don't regress in themselves, while also the system doesn't regress, right? Specifically for scenarios that we've curated within the simulation environment. So yeah, I think we don't necessarily do much of simulation post deployment. All the checks and bounds are sort of sort of the guardrails, so to speak, are before we deploy.
Got it. Some questions around the role of reinforcement learning in your stack and what you're doing.
Yeah, that's a good question. I think reinforcement learning is sort of heavily tuned towards simulation environments and sort of that closed loop. We do a fair amount of RL on the research front, as I mentioned, right? We have a machine learning research team as well that my colleague leads, and so RL is sort of a big aspect there. The difficulty in getting RL for an automated driving scenario is just the complexity of the simulation environment that you need before RL actually starts to make sense. But nevertheless, we do have a lot of research that's happening on the RL front.
A question about what do you think about a hierarchical modular architecture for augmenting new information that comes along and has to be incorporated into the central model?
Sure. By hierarchical, you mean just from a in terms of just the modularity of the stack?
I interpreted that as a modularity of the stack and the way you kind of ensemble models together.
Yep. Yeah. So I think as I'd mentioned, right, there is this notion of traditional AD or automated driving stacks have been modular, and we sort of want to keep some of that modularity in place. Purely because we want to be able to introspect things. We want to see if one module failed over the other. We don't want to see a regression in, say, system performance and don't know where to probe in terms of where do we debug. So we do want that modularity. And that said, right, I think with a lot of this machine learning and sort of deep learning, really part of this stack, we want the models to sort of be composable to the point where we actually can do full end-to-end differentiability. I think that's really where the key is, that you want to compose these models, but you also want to be able to learn the entire system, even while keeping them modular. So we have a few ideas around that, and we're sort of exploring that. Today it's still modular in that there are parts of it that are learned, not necessarily the entire stack is an end-to-end learned stack, but we're sort of eating into that pie as we speak. And like I said, I think the years to come are sort of we're going to get there eventually.
Awesome. Sudeep, thanks so much for joining us, for your presentation, and for your answers to all these questions. Thanks everyone in the audience for the great questions.